So in the last subsection, we introduced the Poisson distribution, and we said it was a useful model for kind of the number of times a thing occurs in a period of time. But then I just wrote down the probability mass function and asked you to take my word for it that it was important. So in this subsection, I'm going to try and explain why the Poisson distribution is a useful and important distribution. And to think about this problem, we're going to think about an example, which is, let's pretend that I'm an owner of a watch shop in Leeds. I sell very expensive watches, so I don't actually need to sell many watches each day. In fact, I sell an average of 4.8 watches each day. So how might I think about modelling this as a random variable? Because some days I'll sell more than 4.8 watches, and some days I'll sell less than 4.8 watches. So how should I model this as a random variable? Well, one way to think about it would be this. There are some number n of people who live in or around Leeds, and each day there's some probability that each one of them will buy my watch. So that would suggest that maybe I should try a binomial distribution to model the number of watches I sell. So I'm a watch owner. I sell an average of 4.8 watches per day. And we're thinking that we might want to model this as binomial NP, where n is the number of people in and around Leeds. And then P will be probability they buy a watch each day. So what should these numbers n and p actually be? Well, one thing I know is that I want the average to be 4.8. And we know that for a binomial distribution, the expectation is n times p. So that means that we'd have to take p equal 4.8 over n, right? Because that would guarantee that the average number of watches I sell is indeed 4.8, the expectation of the binomial distribution. Okay, what should I take n to be, the number of people in and around Leeds? Well, that's a very big number, but it's kind of a bit vague, so I don't really know exactly what it is. So n is just some very large number. So in mathematics, when we have a very large number, what we can do is we can model this as taking a limit n tends to infinity, which is we can make n bigger and bigger and bigger and see if this distribution like settles down to something. And the answer is it does. If we take this binomial n 4.8 over n that we're using to model watches, and if we just take n to be really, really big, turns out this becomes a Poisson distribution with rate lambda equals 4.8. So this is why the Poisson distribution is such a useful model. The Poisson distribution kind of models when there's a large number of things that could happen, but a fairly modest number of them actually do happen, because each one of the large number of things is very unlikely by itself. So we can actually state this as a formal theorem. It looks like this. Fix lambda and let xn be binomial n lambda over n, be a random variable. So note that that's like the watches where we had lambda equals 4.8. Then xn, this binomial distribution, tends towards a Poisson distribution in distribution, by which we mean that the probability here of getting something with this binomial distribution tends towards the probability here of getting it with the Poisson. So when n is very large, the probability of any particular occurrence in the binomial tends towards the probability of that occurrence with the Poisson. So that's quite a formal statement, right? It's got n's in it, and it's got limits, and it's got n tending to infinity. But we can kind of interpret this a bit more informally. Obviously, when we do it informally, it's not exactly a theorem anymore. It's more of a kind of principle, which is when n is large, p is small, and n times p is kind of smallish, then binomial NP is very close to a Poisson lambda where lambda equals NP. That's the idea here, that when n is large, p is small, and np is like smallish, like 1 or 3 or something, then the binomial np is very close to the Poisson lambda. And that's what we had in our example of the watch shot, right? N was some very large number of people living in and around Leeds. P was the very small probability that each of them bought a watch. And then NP was 4.8, a kind of smallish, modest-sized number. I have included a proof of theorem 6.4 in the notes, but because it involves things like limits, which aren't really part of this course, I've marked it as non-examinable. But if you know what limits are from like a course in calculus or in algebra, then you might like to read the proof of this theorem and see if you can understand it. Okay, so here's an example here. Example is a lecturer teaches a module with n equals 100 students. The lecturer estimates that each student turns up at office hours independently with probability p equals 3.5%, 0.035. What is the probability A, that exactly 5 students turn up, and B, that 2 or more students turn up? Okay, well, so the model we have here, right, is that the number of students that turns up is binomial parameters 100 and 3.5%, right? Because there are 100 students, there's a probability 0.035 that each of them turns up independently. So the number that actually turn up is one of these like successes out of n trials thing, which we know is a binomial distribution. So here we've got x being binomial 100, 0.035. So for part A, what's the probability that exactly 5 students turn up? Well, for what we know from a binomial distribution, this is 100 choose 5, 0.035 to the 5, 1 minus 0.035 to the 95. Because 5 of the students do turn up, 95 of the students don't turn up, and there are 100 choose 5 ways of picking the 5 students that turn up. And so if you plug that all into your calculator, apparently you get about 13%, 0.134. What about part B? So part B, this is asking for the probability 2 or more students turn up. Well, this is one of these at least questions, isn't it? The probability at least 2 turns up. So as we know by now, when you've got an at least question, it usually helps to look at the complementary event. So if it's at least 2, then it's not 0 and it's not 1. We can write that. And again, each of these we know from it being a binomial distribution. That's 100 choose 0, 0.035 to the 0, 1 minus 0.035 to the 100, and the other one is 100 choose 1, 0.035 to the 1, 1 minus 0.035 to the 99. And I typed that all into my calculator earlier. You can see some more working in the notes if you like. It came up as about 87%, 0.869. So that's working that out exactly with the binomial distribution. But here we've got one of these cases, right, where n, 100, that's pretty big. P, only 3%, that's pretty small. N times P, 3.5, kind of smallish. This is a case where we could use a Poisson approximation to the binomial. So let's see what happens if we try that. We could approximate this as y being Poisson of 100 times 0.035, which is 3.5. So what would happen if we try to do this with the Poisson approximation instead of the exact binomial? So for part A, we'd have the probability that x equals 5 here, by what we know from the Poisson distribution, e to the minus 3.5, 3.5 to the 5 over 5 factorial. If you plug all that into your calculator, you get about 13% again, 0.132. So if you compare the exact binomial answer and the Poisson approximation, they're very similar. But you can imagine that, especially before computers, doing 0.965 to the power of 95 was quite an unpleasant calculation to do. Whereas this Poisson one with just an exponential and a factorial is fairly easy. Similarly, we can try part B the Poisson way. So again, the probability that x is greater than 2, as before, is 1 minus probability that x equals 1 minus probability x equals 0. So that's 1 minus e to the minus 3.5, 3.5 to the 0 over 0 factorial, minus e to the minus 3.5, 3.5 to the 1 over 1 factorial. Well, 3.5 to the 0 is just 1. 0 factorial, remember that we said that 0 factorial is 1. 3.5 to the 1 is just 3.5, and 1 factorial is just 1. So that's 1 minus e to the minus 3.5 minus 3.5 e to the minus 3.5. A much more pleasant calculation than all these binomial coefficients and numbers that are nearly 1 to enormous powers. And if you plug that all into your calculator, you get 0.864. So again, it's very similar to the exact answer, although not exactly the same. And this was only with n equals 100. If we'd taken like n equals 1,000,000, it would have been incredibly close. So there we're seeing how an exact approach using the binomial approximation, a binomial distribution, gives us the correct answer. But an approximation using the Poisson is just kind of more easy and pleasant to deal with, and would still work even if we didn't know the exact value of n. So that's an example of doing a Poisson approximation to the binomial distribution.